example SVM polynomial kernels, we'll start off with our basic import calls to pull in the things that we need. And then let's go ahead and use the make moons data set. So it's x comma y capital X lowercase y is equal to sk.datasets make underscore moons of n underscore samples equals to 100, comma noise is equal to 0.25, random underscore state is equal to 2. And then let's go ahead and, we've got an error. And noise is equal to, there we go. And then plt.figure. Let's build a figure, plt.plot. We're going to go capital X, open the square bracket, all of our rows for column 0, that y is equal to 0. And then we're going to go capital X, open a square bracket, all of our rows for column 1, given where y is equal to 0. We're going to make those squares. Plt.plot. And now we can go ahead. And so we've got half of our moon. Not bad. Now we just have to get the other half of our moon. And we're just going to go y is equal to 1 and y is equal to 1. We're going to make these diamonds. I'm going to go plt.xlabel. We're going to go x underscore 1, $signs to put it into LaTeX math mode. And then we'll do the same here for 2, and we can go ahead and plot it. And that needs to be a y label. And now we've got kind of 2 half moon data sets. That looks pretty good. And let's go ahead and do an SVM polynomial features. So create a new section. We're going to go SVM. Let's go train model. So we're going to go, again, we're making a classifier. So we're going to go SVM underscore CLF is equal to sk.pipeline. Pipeline. Second pipeline has a capital P. It's always confusing. Open and close my square brackets. I am going to kick down my square brackets to a new line just to help kind of keep things clean. And now I need to open and close a curly bracket, and I'm going to give my pipeline a scalar, and then comma and sk.preprocessing.standard scalar, open and close brackets, nothing else I need, comma, kick it down to a new line. And now I'm going to go quotes SVM underscore CLF. Whoop, I need to get that as a in the quotes SVM underscore CLF, so it's a string, comma sk.svm.svc support vector machine, support vector classifier. Now I want my kernel to equal to poly, and degree is equal to 3, coefficient of 0 is equal to 1, and let's set C equal to 100. And again, C is the scalar that tells me how hard or soft my margins are going to be. And now I've been able to build that pipeline. So I'm going to go svm.clf.fit of x comma y. Let's go ahead and train it. SVM has no attribute. Oh, yep. Underscore CLF dot fit. And now I've trained my model with that pipeline. So what I want to do now is kind of plot the result. And to do that, I need to make a 2D space for all of my cool plots that we're about to make. So let's scroll down a bit. So now I'm going to go x1 is equal to np.lin space of -2, 3, 200. Get rid of my space there. And x2 is equal to np.lin space of -2, 2, 100. And x1 underscore grid, x2 underscore grid is equal to np dot mesh grid of x1, x2. Let's go ahead and run that. Spelled lin, no E. There we go. And now we're going to calculate the binary decision and prediction values. X2 is equal to np.vstack. Open and close my brackets. Now I need to make it a tuple. So there's going to be another open and close brackets there. x1 underscore grid dot ravel, ravel, open and close brackets, and x2 underscore grid dot ravel, open and close brackets, and then you should have another bracket and another bracket. So on the backside there, you're going to have 3 right brackets, dot t to give it a transpose, and that's just going to put x2 into into an array that is 2 columns and 20,000 lines. And now I can go y underscore prediction. Again, that's the prediction of my target is equal to svm underscore clf dot predict capital X2. And this one needs to be a capital X. I apologize. That needs to be a capital X2. A capital X numerical 2. Capital X numerical 2. Okay, so I'm going to predict that, but now I want to reshape to get it into the right form. Reshape based on the grid of my x1 underscore grid dot shape. I have an extra curly bracket, F5, and then we have a Y prediction here. So that should be looking close to what we want. And now we need Y underscore decision. That's going to be the line that we draw down the middle. is equal to svm underscore clf dot decision underscore function, open and close x2 dot reshape to lowercase x1 underscore grid dot shape. And again, that's just giving me the shape of x1, which is then driving the shape of my y decision. And so now my y decision is a 100 by 200. So what I've done is I've created all of these grids. And now I can go ahead and plot the grid. So let's go ahead and plot the results. And so first we're going to do plt.figure, just open and close a figure. And now let's go ahead and go plt.contour, C-O-N-T, contour F. And so for contour F, I need to bring in x1 underscore grid, comma x2 underscore grid, comma y underscore prediction, comma c map equals plt dot cm dot brg. That's just setting a color map. I'm going to go alpha equals 0.2, and that's just setting some amount of transparency on my data set. So I've now gone ahead, and x and y gives me my locations, and y prediction gives me my my results. So another thing that we can do now is I'm going to come up here and I'm going to copy plotting this data, and I'm going to move it for the time being down here because I want it to show up on top of my contour lines. So now I have that data, and I have the kernel trick that shows that it can, accurately make those predictions. We can go ahead and add a few more things. Maybe we want to get some contour lines because the contour lines allow us to see the variations of where we're predicting. So first, let's build some con underscore lines, and you can do whatever contour lines you want. I'm going to go -30, comma -20, comma -10, comma 0, comma 10, comma 20, comma 30, but it doesn't matter what you pick. And now I can do plt.contour F. x1 underscore grid, comma x2 underscore grid, comma y underscore decision, con underscore lines, comma c map is equal to plt.cm.brg. We'll see if we can get away with that. And let's see if that gives me so that gives me these nice, very aggressive kind of contour lines on top of that. And if I want to actually get real contour lines, what I can do is get rid of the con F. So I can just go ahead and do plt.contour again x1 underscore grid, just contour. So we're just going to put the lines on top. x2 underscore grid, and then y underscore decision, and then con lines, con underscore lines. And that should give me these actual lines on top. I am going to add this alpha here. Just to make it a little bit softer on the eyes. Otherwise it's just a very hard color scheme. And that shows you something that you can do with the SVC kernel as a way to use a lower number of polynomials to process your data.